Assalamualaikum and good day everyone. So in this lecture you are going to learn the concept of calorimetry. So what is calorimetry? Calorimetry is the experimental technique to determine enthalpy of reactions. Okay, so in the other words we can say that calorimetry is the process of measuring the amount of heat released or absorbed during a chemical reaction. So in this concept, you can determine whether the reaction will undergo exothermic reaction, which is release heat, or endothermic reaction, which is absorb heat. Okay, and this concept of calorimetry is actually plays quite a large part in our everyday life. Okay, maybe the best example will be like the one maintaining functions in our body, such as maintaining the body temperature. Okay, and then a device that can be used to measure quantities of heat, or a device that can be used to measure the amount of heat absorbed or released from the reaction, we call it as calorimeter. Okay, so in order to measure the heat of a reaction, the reaction must be isolated. So in the previous lectures, okay, in the first lecture actually, you have learned a few types of system. We have open system, closed system, and isolated system. So in order to find enthalpy of reaction, in order to know the enthalpy of certain reaction, the system must be isolated system, so that there will be no heat is lost to the environment. Okay, so this can be done by using calorimeter. Okay, why? Because calorimeter insulates the reaction, okay, to better contain heat. So calorimeter will help to prevent the loss of heat to the surrounding. Okay, prevent the loss of heat and mass to the surrounding. So we do have two types of calorimeter. Okay, we have simple calorimeter, or the other name is constant pressure calorimeter. So simple calorimeter is usually to be used in order to measure heat of neutralization or enthalpy of neutralization. And the other type is calorimeter bomb or bomb calorimeter, which is a constant volume calorimeter. And this kind of calorimeter will be used in order to measure enthalpy of combustion reaction. So simple calorimeter, usually we will deal with solutions, reactants, and for bomb calorimeter, usually involving gases sample. So that are the differences between these two calorimeters. Alright, now, so before we go deeper into the calorimetry concept, so let's recall a few basic concepts of thermochemistry that you have learned in the previous lecture. Okay, suppose that we have a combustion reaction. Okay, so combustion reaction, so this is the reaction or the system. Okay, so we know that combustion reaction will release energy because it is exothermic reaction. But do we know how much energy is being released from the reaction? Do we know exactly the amount of energy released from this combustion reaction? So maybe sometimes we couldn't find the amount of energy released from the reaction directly, okay, from the reaction itself. Why? Because maybe we have lack of information regarding the reaction. So in that case, we are unable to calculate the enthalpy of the reaction or the amount of energy released from the reaction directly. Okay, but if we do have another terms, okay, in thermochemistry, that is the surrounding. Okay, so let's say we have the human as the surrounding. Okay, all right, now, so when the human approaching the combustion site, so the human can feel the warmth. Okay, and the human can tell whether that reaction, the combustion site, is very hot or it is just warm. Okay, so what I'm trying to say here is maybe in order to find enthalpy of reaction, in this case combustion reaction, we cannot directly calculate from the information we have from the reaction itself. But maybe we can calculate the enthalpy of the reaction from the information we have from the surrounding. Okay, because the concept between reaction and surrounding is the amount of energy released from the reaction will be absorbed by the surrounding. So by having or by knowing the information from the surrounding, it is able, okay, it makes us possible to find enthalpy of reaction, of certain reaction. So that is the relationship between reaction and surrounding. So this is the example of simple calorimeter. So as you can see from the image, the simple calorimeter is made up from styrofoam cups. Do you know what is styrofoam cups? Yes, the one that you use to drink tea or coffee. So that's why this simple calorimeter is also known as coffee cup calorimeter. Why coffee cup calorimeter? Because we use styrofoam cups. Okay, so the outer styrofoam cup insulate the reaction mixture from the surrounding. So it is assumed that no heat is lost to the surroundings. Okay, so inside these styrofoam cups, we put our acid and base and let the neutralization reaction occurs, okay, inside this reaction mixture. Alright, and you have to make sure we have to cover this styrofoam cup with any cover, any type of cover, okay, just to make sure there will be no heat or mass lost to the surrounding. So in this reaction, it is assumed that heat released by the reaction inside this styrofoam cup is absorbed by the solution and the calorimeter. Alright, so heat released by the reaction, this is from the reaction, is absorbed by solution and the calorimeter. So these two will be the surrounding. Okay, so in this concept, you have to bear in mind there will be no heat loss to environment. Okay, so when there is no heat loss to the environment, so hence we can calculate enthalpy of this reaction. Okay, so how to calculate enthalpy of the reaction? We must get it from the information we get from the surrounding. The second one is bomb calorimeter, okay, or constant volume calorimeter. So why constant volume calorimeter? Because the pressure will be changes, okay, during the entire time of the reaction. Okay, so in bomb calorimeter, okay, so here we have a reaction chamber whereby we put the sample and the combustion reaction will occur, okay, in this part. So again, when the combustion reaction occurs in this part, so the heat loss from the reaction will be absorbed by the surrounding. So in this case, we have two types of surrounding, that is the water and calorimeter. So again, in this bomb calorimeter, you have to assume that there will be no heat loss to the environment. Okay, there will be no heat loss to the environment. So all the system will be isolated system. Okay, so same with simple calorimeter. Okay, so next we go to the concept of the calorimetry, another concept of calorimetry, that is specific heat capacity C, or sometimes we can use the symbol of S also, and heat capacity, which is capital C. So what is specific heat capacity? It is the amount of heat required to raise the temperature of 1 gram of the substance by 1 degree Celsius, and the unit will be in joule per gram per degree Celsius. And the heat capacity, capital C, is the amount of heat required to raise the temperature of a given quantity of the substance by 1 degree Celsius, and the unit will be joule per degree Celsius. So for specific heat capacity, it has something to do with mass, okay, with 1 gram. Okay, and for heat capacity, okay, we just measure for the given quantity, okay, of the reaction. So according to the basic principle in calorimetry, the heat released from the reaction equals to the heat absorbed by the surrounding. Okay, so in order to know how much energy released from the reaction, we can get it from the information we obtain by the surrounding. Okay, why is that so? Why is it so? Because the heat released from the reaction is negative Q reaction. The value will be in negative form. And heat absorbed by the surrounding will have the same value like the reaction, but it is in positive form. So that's why I mentioned in the previous slides, the amount of energy released from the reaction is actually equals to the amount of energy absorbed by the surrounding. Okay, so what makes them different is actually the notation. Okay, energy released from the reaction, okay, we will put the sign negative, and energy absorbed by the surrounding will be using the positive sign. Okay, so this too shows that how much energy released from the reaction will be absorbed exactly the same by the surrounding. So for example, if one combustion reaction release 500 kilojoule of energy, so the surrounding will absorb the same amount of energy, which is 500 kilojoule. Hence, by knowing the amount of heat absorbed by the surrounding, so we will able to find the energy released from the reaction. In bomb calorimeter, the heat released from the reaction equals to the heat absorbed by the surrounding, meaning that how much energy released from the reaction will be absorbed by the surrounding with the same amount. So what differs between them is only the notation. So the heat released by the reaction will be in the negative form, and the heat absorbed by the surrounding will be in positive form. Okay, but the amount or the value will be exactly the same. So the heat absorbed by the surrounding, okay, can be in these 3 ways. So for the surrounding, we can have both water and calorimeter as the surrounding. So if we have both water and calorimeter as the surrounding, so the formula will be MW, CW, and delta T, plus capital C of calorimeter and delta T. So MW is the mass of water or solution. CW is the specific heat capacity of water or solution. Capital C is for calorimeter, and delta T will be the temperature change. The next one, the surrounding could be the water only. So if the water act as the only surrounding, the formula will be Q surrounding equals to MC delta T. So M is for water or solution, and small c here is for water or solution. Delta T will be the temperature changes. And if we have calorimeter only as the surrounding, so the formula for the Q surrounding will be capital C delta T or MC delta T. So M is for mass of calorimeter. The small c will be the specific heat capacity of the calorimeter, whereby the delta T here will be the temperature changes. Okay, so in order to find the heat released from the reaction, we can get from the heat absorbed by the surrounding. So these are the 3 formulas that we can use in order to find the heat absorbed by the surrounding. Okay, so in order to find enthalpy of this reaction or energy released from this reaction, okay, we can get the information from the surrounding. We can calculate from the surrounding, because surrounding will absorb the same amount of energy released by the reaction. So again, we have 3 ways to calculate energy absorbed by the surrounding. That is, if we have both water and calorimeter as the surrounding, so the formula will be Q surrounding equals to M water, small c for water, delta T, plus capital C for calorimeter and delta T. And if we have the water alone as the surrounding, so the formula will be Q surrounding equals to M water or solution, C water or solution times delta T. And if we have the calorimeter alone as the surrounding, so to get the heat absorbed by surrounding, the formula will be capital C calorimeter times delta T, or mass of calorimeter times small c of calorimeter, which is specific heat capacity of calorimeter, and delta T. So when you are dealing with the problems later on, you have to identify which formula to be used in your calculation, okay, whether the first one, second, or the third. As for simple calorimeter, we will use the simple calorimeter in order to study the enthalpy of neutralization. So after we mix both acid and base into the styrofoam cup, reaction will occur between those two. So when reaction occurs, it will release certain amount of energy to the surrounding. So surrounding in this case will be the solution. So in order to find enthalpy of neutralization or the heat released from the reaction, we must get it from the energy or heat absorbed by the surrounding. Okay, so since energy release will be absorbed by solution as the surrounding, so the formula will be Q surrounding equals to MW times CW delta T, or M solution, mass of solution, times specific heat capacity of the solution times delta T. Okay, so let's see this example. The combustion of 1.435 gram of naphthalene causes the temperature of the 500 gram of water in the bomb calorimeter increases 5.67 degrees Celsius. Calculate the enthalpy of combustion of naphthalene if the heat capacity of the calorimeter is 8077 joule per Kelvin and the specific heat of water is 4.184 joule per Kelvin. So, in this example, in this question, we have this info, we have this information, we have this one, we have this one, and this value. Okay, the first value here is mass of naphthalene. Okay, so what is naphthalene in this example? Okay, in this reaction, naphthalene is the reactant that we burned, okay, in the bomb calorimeter. So naphthalene is the sample that we burn in the bomb calorimeter. Okay, so that is our reaction actually. Okay, combustion of the naphthalene. And then we also have 500 gram of water. So what is water? Definitely water is our surrounding. So here we already have the mass of the surrounding. Okay, and then it is mentioned that this reaction is done in bomb calorimeter. This experiment is done in bomb calorimeter. Okay, so this value is the delta T. Okay, heat capacity of calorimeter. So here we have the capital C of calorimeter and specific heat of water. So here is the small c of water, specific heat capacity of the water. Okay, now in this question, so what will be our surrounding? We have water. Okay, we have mass of water. And also we have information that is heat capacity of the calorimeter. Okay, now, so if in the soalan, you've been given the information regarding water and calorimeter, meaning that our assumption is energy released from combustion reaction will be absorbed by the surrounding, and the surrounding will be both water and calorimeter. Why is that so? Because we have information regarding mass of water and also capital C of calorimeter. So that is the way to assume, okay, in our calculation. Since we have both information regarding water and calorimeter in the question, so we can assume that our surrounding will be both water and calorimeter. So in order to calculate the heat of reaction, so firstly you have to calculate heat of the surrounding. So the formula will be Q surrounding equals to capital C of calorimeter times delta T plus mass of water, specific heat capacity of water times delta T. And then you insert the values.
Okay, the delta T given in the question is in degrees Celsius. Okay, but the difference in temperature will be the same whether in degrees Celsius or in Kelvin. Okay, plus mc delta T, so we have mass of water 500 grams, specific heat capacity of water, and the delta T. Okay, so we can cancel this unit, gram and per gram, Kelvin and per Kelvin. So for the Q surrounding, you will get 57.649 joule. Or to simplify your answer, you can just find it in kilojoule. So 57.6469 kilojoule.
Okay, so this is actually the amount of heat absorbed. Okay, the amount of heat absorbed by the surrounding. So in order to find heat released from the reaction, okay, so let's recall the concept between those two. Heat released from reaction equals to the heat absorbed by the surrounding. Okay, so how to relate between those two? It is Q reaction, which is energy released from the reaction, equals to plus energy absorbed by the surrounding, or heat absorbed by the surrounding. Okay, so heat released by the reaction equals to heat absorbed by the surrounding. So now we already have the amount of Q surrounding. So from this formula, you can find the heat released from the reaction, which is Q reaction. So our Q reaction will be negative 57.6469 kilojoule. Okay, let's go back to the question. So the question asks you to find the enthalpy of combustion of naphthalene. So let's recall the definition of enthalpy of combustion. Enthalpy of combustion refers to 1 mole of naphthalene burnt in excess oxygen. Okay, 1 mole of naphthalene burnt in excess oxygen. But now in the question, we have 1.435 gram of naphthalene. So is this 1.435 gram of naphthalene equals to 1 mole? Okay, so we are not really sure about that. So let's calculate the number of mole of the naphthalene first. So N of naphthalene is the mass in gram divide its molar mass. So you will have 0.01121 mole. Okay, so from this question, burning of 1.435 of naphthalene will cause this water and calorimeter absorb this amount of energy. So hence, from this energy absorbed by the surrounding, we can get the amount of heat released by the reaction. But the amount of heat released from this reaction is actually correlates to this amount of mole, meaning that 0.01121 mole of naphthalene burns to release this amount of energy. So in the form of ratio, okay, we can write it down as 0.01121 mole of naphthalene burns to release 57.64 0.469 kilojoule of energy. But the question asks you to find the enthalpy of combustion. Okay, enthalpy of combustion refers to the 1 mole of naphthalene burns in excess oxygen. So in order to find enthalpy of combustion, actually you are needed to find the energy released for 1 mole of naphthalene burnt. Okay, so from here you will get enthalpy of combustion. So to get your answer over here, you may simply darab silang. Okay, so hence the formula will be delta H combustion equals to Q reaction over N of naphthalene. Okay, so the bottom part here will be the burn sample. Okay, the burn sample. So now, by substituting the values, so this is our Q reaction. The whole part here is the Q reaction. Okay, so the one with negative is the Q reaction. So Q reaction will be negative 57.6469 kilojoule divide with 0.01121 mole. So you will get kilojoule over mole. Your answer will be in kilojoule per mole. So this answer is consistent with the enthalpy of combustion. Why? Because enthalpy of combustion refers to 1 mole of burning sample, of the burn sample, and since we are burning 1 mole of the burn sample, so the unit must be in kilojoule per mole. Suppose that we have this problem. So in an experiment, 0.1 gram of hydrogen and excess of oxygen were compressed into a 1.0 liter bomb calorimeter and placed into a calorimeter with a heat capacity of 9.08 times 10 power 4 joule per degree Celsius. The initial temperature of the calorimeter was 25 degrees Celsius, and finally it increased to 25.155 degree Celsius. Calculate the amount of heat release and enthalpy of combustion. So the amount of heat release is our Q reaction, and enthalpy of combustion is delta HC. So these are the two important things that you have to find in this question. You need to find the Q reaction and also the enthalpy of combustion, delta HC. So in this soalan, so what will be our surrounding? Okay, so from the sentence, can you predict what will be our surrounding? Do we have mass of water in the question? No. Do we have heat capacity of the calorimeter? Yes. Okay, we have heat capacity of the calorimeter only. So we can make assumption that energy released from this reaction will be absorbed by the calorimeter only. So calorimeter will be the only surrounding in this problem. Alright, now, so let's work out for the solution. So to answer question A, which is to find the amount of heat release, so firstly you have to find from the Q surrounding, that is the heat absorbed by the surrounding, and the formula will be capital C of calorimeter times delta T. So why we use this formula? Because we just assume that we have calorimeter as the only surrounding. And the delta T will be the final temperature minus the initial temperature. So you will get your answer. I simplify into kilojoule per mole. This is my value in kilojoule. Sorry, I simplify my answer into kilojoule. Okay, so this is my answer in kilojoule, 14.1 kilojoule. Okay, now, so to get the heat release from the reaction, so we will use this formula. Negative Q reaction equals to plus Q of the surrounding. So hence the Q reaction will be negative 14.1 kilojoule. Okay, so this is the answer for heat release from the reaction. All right, or you can also simplify, you can also give your answer in terms of sentence, that is heat release is 14.1 kilojoule. So by writing this sentence, it is not necessary to put the negative in front of you. Why? Because it is mentioned in the first sentence, heat release. So I understood that release meaning that this value is actually in negative. But if you just write your jawapan in these terms, okay, in these terms, so you have to put Q reaction equals to negative 14.1 kilojoule. But in sentences, okay, you just mention the heat release and the value only, okay, without the sign over here. All right, so this is the amount of energy released from this reaction. Okay, so we have answered question A. Okay, for question B, you are needed to find the enthalpy of combustion, okay, from this reaction. So in this reaction, we have burned 0.1 gram of hydrogen. Okay, we burn 0.1 gram of hydrogen. So when you are about to find enthalpy of combustion refers to the heat release when we burn 1 mole of the sample. But now in this question, we burn 0.1 gram of the sample, okay, which is not equals to 1 mole. Is that so? Is that really so? Is that really this 0.1 gram is not equals to 1 mole? Okay, so just you have to calculate the number of mole of the hydrogen gas. So for question B, so first of all, write the combustion equation between hydrogen and oxygen gas. Okay, and please make sure you have balanced the equation well. So we will have 1/2 over here. All right, now we have burned 0.1 gram of the sample. So the first step is we have to find the number of mole of the burning sample. So the mass over the molar mass of H2. So you will get 0.0496 mole. Okay, so meaning that burning of 0.0496 mole of hydrogen gas will release negative 14.1 kilojoule. Okay, so this is obviously not yet the enthalpy of combustion. Why? In order to find enthalpy of combustion, we must make this mole as 1 mole. Okay, so in order to find enthalpy of combustion, okay, which is for 1 mole of hydrogen gas burned in the sample, so you can simply doing the darab silang. So the formula will be delta HC equals to Q reaction over N of your burning sample, which is hydrogen. Okay, so this is our Q reaction, which is negative 14.1 kilojoule over this mole. So you will get your jawapan in negative 284 kilojoule per mole. Okay, so this is the amount of energy released when we burn 1 mole of hydrogen gas. So this is the example of calculation using styrofoam cup calorimeter or simple calorimeter. And in this question, you are going to find the enthalpy of neutralization between hydrochloric acid and aqueous ammonia. So in this question, we can assume that the energy released from the neutralization reaction will be absorbed by the surrounding. And as this is neutralization reaction and we are using a styrofoam cup calorimeter or simple calorimeter, we can assume that the heat released from the reaction will be absorbed by the surrounding, that is solution. So solution will be the only surrounding for this reaction. So the first step is by finding the heat absorbed by the surrounding. So Q surrounding equals to M solution times C of solution times delta T, or M water times C of water times delta T. Okay, so how we can get the mass of the solution? So previously in this soalan, we already have 200 ml of hydrochloric acid and 100 ml of aqueous ammonia. Okay, so mixing these two, we will get solution. So this is the density of the solution. So by using density formula, density equals to mass over volume. Okay, so we have the density value, which is 1.0 gram per ml, m over volume, which is 300 ml. Okay, so the mass will be, mass of solution will be 300 grams. So this is a way to convert the volume of solution into mass of solution or mass of water. The delta T will be final temperature minus initial temperature. So we have 8.3 Kelvin. Okay, so by using the formula, negative Q reaction equals to plus Q of the surrounding. So the Q reaction, the heat release equals to negative 10.4082 kilojoule. So in order to find enthalpy of neutralization, so according to the definition, enthalpy of neutralization is heat release when 1 mole of water is formed from the neutralization of acid and base. So this 1 mole, okay, must be put on the water, which is on the product part. Okay, so this is 1 mole of water. Alright, now, so in order to find delta H neutralization, the formula will be the Q reaction over N of water. So do we have N of water in this soalan? The answer is no. Okay, we didn't have any mass of water that could lead us to find the end of water. Okay, so in order to get the end of water, so you must get it from the reactants, okay, from these either two reactants. So we already have the molar and volume of these two reactants. So by calculating N equals to mV, you will find out the HCl will has 0.2 mole and the other reactant will has 0.05 mole. So this two is actually the available amount. So in order to find the N of water over here, okay, you can simply do the stoichiometric ratio, okay, with any of these two reactants. But before you do that, you have to find the limiting reactant.
So let's find the limiting reactant first. So assume that HCl as limiting reactant. So according to the balanced chemical equation, 1 mole of HCl will react with 1 mole of ammonium hydroxide. So if we have 0.2 mole of HCl, you have to find the new N for ammonium hydroxide. Okay? So we will have 0.2 mole of ammonium hydroxide. So this 0.2 mole is actually the needed mole of the ammonium hydroxide in this reaction.
So by comparing this needed amount with this available amount, okay, so it is clearly, we can clearly state that the actual limiting reactant is actually ammonium hydroxide, because we need as much as 0.2 mole but we only have 0.05 mole. So our real limiting reactant will be ammonium hydroxide. So now, after you have got your real limiting reactant, so now you can simply relate this limiting reactant with this water in order to get the number of mole of the water. So from the ratio, 1 mole of ammonium hydroxide equals to 1 mole of water. So if we have 0.05 mole of ammonium hydroxide, so the N of water here is actually will have the same amount, which is 0.05 mole. So from the values we have obtained from the calculation just now, 0.05 mole of water is produced in this neutralization reaction. So this neutralization reaction that release 10.4082 kilojoule of energy is actually will form 0.05 mole of water. So in order to find enthalpy of neutralization, we must refer to 1 mole of water formed from this neutralization reaction. So in order to get the enthalpy of neutralization, so we need to have the Q reaction over N of water. So this is our Q reaction. So by substituting the values, so you will get negative 208.164 kilojoule per mole. Okay, so this is your answer for neutralization, enthalpy of neutralization, meaning that this is the amount of energy that will be released in order to form 1 mole of water. Okay, but the one that you calculate from the calculation just now, okay, this is the amount of heat release when 0.05 mole of water formed from the reaction.